All right, welcome back from the break. Now let's try to apply the rules involved in naming organic chemistry. I've given us 5 sets of rules before now. Let's see how we can apply those rules to name this compound on the board. Now let's take a look at the first one. We have 1, 2, 3, 4, 5, 6 carbon atom as a straight chain. This is a straight chain hydrocarbon. Now the root or the parent hydrocarbon here is how many? Is 1, 2, 3, 4, 5, 6. And this compound belongs to alkane as homologous series. So now our parent hydrocarbon here is what? Is hexane. 1, 2, 3, 4, 5, 6. 6 carbon atom, hexane, called the parent hydrocarbon. This is the parent hydrocarbon, okay, hexane. Now note that and keep somewhere. Now let's start our numbering. Now we have 2 substituents attached to the parent or the root hydrocarbon, which is our hexane. Don't forget, hexane is our root hydrocarbon, so don't forget it. But we have 2 substituents. The one is the methyl group CS3. The other one is the ethyl group C2H. Don't forget, methyl is from where? It's from methane. Alkyl group, methyl, ethyl. Now, at the cost of numbering your carbon atom, you must give the lowest possible number. Don't forget. So if you start counting your carbon atom from this side, you have 1, 2. Because we have the first substituent attached to carbon 2, 1, 2. If you start from this side, you have 1, 2, 3. So here is longer, but here is closer. Here gives us what? The lowest possible number to the carbon chain. So the actual side of our numbering begins from this side. We have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon what? 6. Okay. Now, don't forget the rule that says you must follow what the alphabetical word order if there are more than 2 substituents present in an organic compound. So we have the first one called methyl. This guy here is called methyl, don't forget, from methane, whereas this guy here is called ethyl from where? From ethane. Now, if you look at it very well, we have letter E before what? Letter M. Alphabetical order. And each of these are given what? Their respective number to their carbon in which they have been attached. You give reference to alphabetical order of the substituents present in the homologous series. We have really gotten our parent hydrocarbon, which is 6 hexane, because it belongs to N functional group. All right, so we have 2 substituents, methyl and what? Ethyl. But ethyl is attached to what? It is attached to carbon 4, whereas the methyl is attached to what? Attached to carbon 2. So you start with the what? Ethyl. Which carbon atom? 4. We have 4 ethyl, followed by what? 2. Because methyl is attached to what? Carbon 2. 2 methyl. Then your parent hydrocarbon, which is hexane. So that is the name for this compound. 4 ethyl, 2 methyl hexane, which is your parent hydrocarbon. All right, let's try the next one. Now this falls under the category of cycloalkane. Okay, so this is 1, 2, 3, which means that it is a propane. Normally it is propane, but because it forms a ring, it becomes what? Cyclopropane. So this is a cyclopropane on its own, but there is one substituent attached to it, which is methyl group. Okay, so you start from here, 1 methyl cyclopropane. Carbon 1, carbon 2, carbon 3. So your numbering starts from 1, 2, and 3. So the name here is 1-methyl cyclopropane. You can see it's very simple. 1-methyl cyclopropane. 1, 2, 3. All right. Let's take the next example. Sorry, this is number 3. Example 3. We have, I will not waste much time again because I've explained the first 2. Now look at the root hydrocarbon. How many do we have? 1, 2, 3, 4, 5, 6. So this is hexane as the parent hydrocarbon. Good. So how many substituents do we have? We have 4. 1, 2, 3, and 4. Now this is a mixed substituent. 1 organic, but 2 inorganic. But these are the same. So where you start numbering from? If you check very well, this is still 1, 2, carbon 2, 1, carbon 2. So if you start numbering from from this side, it is wrong because you give preference to what? Inorganic first before the organic compound when they have mixed substituents. In this case, your numbering will not start from this side. Rather, it will start from the one that contains the inorganic substituents. So this is carbon 1, carbon 2, carbon 3, 4, 5, and what? 6. Having done that, don't forget your parent hydrocarbon is 6-hexane. Now let's give numbers to the substituents. Alphabetical what? Order. Now bromine, B come before what? Before chlorine. So you start from the bro before you get to the organic substituents. That will give us what? Bromine is attached to carbon 3. So the name now starts with what? 3-bromo hyphen followed by what? Chloro. And there are 2. So we now call it 2,2 because one attached to the same carbon, another to the same carbon. So 1 down, 1 up. So this is 2, 2. Now when they add 2, what do we call them? We call di. Because we have the 2 of the same in one carbon atom, we call the word di. So this is 2, 2 dichloro. Chloro what? Look at another one here. Methyl group. Chloro. This methyl is attached to which carbon atom? Carbon 5. So we have chloro 5 methyl. Oh, there's no space here. Methyl. Then your parent hydrocarbon is what? Is hexane. So this is the name for the compound. 3-bromo 2,2,2,2-dichloro 5-methyl then hexane as your parent hydrocarbon. That's the name. Okay, this one the same thing. 1, 2, 3, 4, 5. This is pentane. Parent hydrocarbon is pentane. How many substituents do we have? We have 1, 2, 3, 4, but 2 are the same. This is ethyl, this is methyl, this is iodo. Where your counting starts from the side that contains what? The halogens group. If you start from here to count is wrong, so you start from here. Preference to what? Inorganic substituents. So that will give us what? That will give us what? 2. This is 1, 2, 3, 4, 5. So 2. This is called iodo from iodine. 2-iodo. A come before me. 2-iodo. 3,3 because we have 2. Then di-ethyl. This is called ethyl. C2H5 is ethyl. Di-ethyl. Then 4-methyl. Then the parent, which is pentane. That's the name for this one. Then the other one, this is functional group. In. This is an in functional group. So your counting is from 1, 2, 3, 4, 5. Pentane. But because of this, it's called what? Pentene. So which carbon atom do we have the functional group? Carbon 2. Okay, so carbon 2. So your numbering will not start from here because you give us the longest possible number. But here is the lowest possible number. 1 and 2. Then 1, 2, 3 is too far. Your counting begins from here. So we have 1, 2, 1, 2, 3, 4, 5. We have, this is pent. Go to your functional group in from alkene. Pent. Which carbon atom do we have the in? Carbon 2. We have pent 2 in. That is all. Pent from where? 1, 2, 3, 4, 5. Pentene. To which functional group? In. To carbon what? Carbon 2. So we have pent 2 in. All right, so this one, we have two functional groups here. One is the real functional group, other act as what? As a substituent. So you give preference to the longest chain. Your counting is from here. This is null group, alkanal, CHO. So your parents at your carbon here is 1, 2, 3, 4, 5. This is what? Pentanal. So we have a substituent as carbon what? Carbon 3. So that the name here will becomes 3-hydroxy. 3-hydroxy, followed by what? The parents at your carbon, pentanal. Or you can say pent-1-nal. Either pentanal or pent-1-nal. 3-hydroxy, 1, 2, 3, 4, 5, pentanal. Okay. This is carboxylic from alkanoic. One acts as a primary functional group, one acts as what? As a substituent. So your counting will not start from here. We'll start. This is the original functional group. This is group 5. Give preference to what? To the functional group. So we have 1, 2, 3, 4, 5. So our organic nomenclature here will be what? Don't forget the alphabetical order. This is hydroxy, this is carboxylic. So carboxy comes before what? The hydroxy. Now, if this functional group happens to be a prefix, it is called carboxyl. If it is suffix, it's called what? Carboxylic. So it's called what? Noic acid. So 1, 2, 3. 3 carboxyl. 3 again, hydroxyl. Then the actual parent hydrocarbon, 1, 2, 3, 4, 5. This is pentanoic acid. Pentanoic acid. All this, if you follow the rules, you will not have issue on naming any organic compound. Then this is number 6. This is number 7. This is number 8. Then number 8. 1, 2. This is your parent's hydrocarbon. Don't forget. Parent's hydrocarbon. This is a 10. We have 1, 2, 3, 4 substituents of the same class. Are we together? So that will give us what? This is the parent's alkane. 1, 2, 3, 4. So we have 4 of the same kind of what? Substituents. This is 1, 2, 3. No, not 2. It's 1, 1. 1, 1, 2, 2. Tetra. Tetra means 4. 1, 1. If you start from here, 1. Start from here, 2. So anywhere, 1, 1, or can be 1, 2, anywhere. 1, 1, 2, 2, tetra, chloro. Parent's hydrocarbon is what? Is a 10. So we have 1, 1, 2, 2, tetrachloro, a 10. Then the last but not the least, this is from an alkanoate family or an ester. So if you look at it very well, this happens to be, this acts as a substituent, whereas this acts as the main organic functional group. So you start from the substituents. 1, 2, 3 is called propyl from propane. Then 1, 2, 3 is what? Is noate, alkanoate, because of the presence of this functional group. This is alkanoate called esters, COO. So this is your substituents. Now without this compound is called propanoate on its own. But because we have a substituent here, you start with substituent and then hang up with what? With the actual organic compound. So this is propyl, propanoate. From where? An alkanoate functional group, or you call it ester. Propyl, 1, 2, 3, propyl. Then propanoate, because it has 3 carbon atoms. 1, 2, 3, propanoate. So if you follow the set of rules given earlier before now, there is no organic compound given to you, you will not be able to name. These are just few. Consult textbooks, past questions, you see more, and to try to name them by yourself. Okay, the next subtopic is isomerism. Now, isomerism is the occurrence of organic compound with the same molecular formula but different structures. Any organic compound that possesses the same molecular formula but different structure is known as, that process is called what? Isomerism. Then the real compound themselves are called what? Isomers. The compounds are called isomers. So this is just a process, a phenomenon in which organic compound contain the same molecular formula but different what? Structures. Now, as the number of carbon atoms in the molecule increases, the number of isomer also increase. For example, hexane will have isomer of 5, butane 2, and so on, because butane contains 4 carbon atoms with 2 isomers, hexane 6 carbon atoms with 5 isomers with its normal straight chain hydrocarbons. Let's proceed. For example, okay, hexane, I said before now, hexane has the following isomers. The N-hexane, 3-methylpentane, we have 2-methylpentane, 2,3-dimethylbutane, then 2,2-dimethylbutane. If you follow the rules given for this, you can be able to draw the structure for all of this compound. First of all, get the parent hydrocarbon, which is pentane, 5 carbon atom. Then look for carbon 3 and attach methyl group. That is a structure. Something applicable to this one. Parent hydrocarbon is pentane, which is 5 carbon atom. Locate carbon 2 and attach the methyl CH3 group. You have the structure. This one we have 2, 3. So carbon 3 and carbon 2 will contain methyl group, while the straight chain reduces to what? To butane, and so on. So it's very simple. You follow the rules given before now. All right, then we have different types of isomerism. We have structural isomerism, we have geometric isomerism, we have optical isomerism. At this level, we will streamline to these 3: structural, geometric, and what? And optical. Now, what are structural isomerism? Now, this differs on the different arrangements of hydrocarbon. It can be, for example, but2-ene, but1-ene, 2,3-dichloroethane, 1,2-dichloroethane of the different structures. Now, these occur when the isomers differ only in the arrangement of atoms or groups within the molecule without any reference to space. It can be further classified into 3. So under structure, we have 3, which are the chain. First one is chain. We have chain, we have the positional, we have the functional. Let's start with the first one, the chain, or also known as skeleton or nuclear isomerism. Now, this type of isomerism is due to a difference in the nature of the carbon atom, whether straight or branched, which form the nucleus of the molecule. Example, butane. We have butane, I have 2-methylpropane. This compound, they have the same molecular formula, butane. Then we have 2-methyl. If you check, they have the same molecular formula, but different structures. We have pent1-ine, and also what? 3-methyl-but1-ine. So this is just a branch of this, but they have the same molecular formula, but different what? Structure. The next one under structural is positional isomerism. This is due to the difference in the position of the side chain atom or group, or an unsaturated linkage in the same carbon, e.g., but1-ene, but2-ene. It's just a shift. It's just a shift. But1-ene. For example, let me illustrate that one for you. I think I can clean this one to have space. It's just a shift in the functional group. But1-ene. But is the parent with 4 carbon. 1, 2, 3, 4. Because of ene contains double bond. 1, it can be here, it can be here. If you start from here, your double bond is attached to this place. If you start from this side, it is attached to this side. So all others are your normal hydrogen atom attached to it. So this is but1-ene. Then for the but2-ene, just shift this to this position, that's all. That shows that the functional group now moved from carbon 1 to carbon 2. That is all about positional functional group. The next one is functional isomerism. This happens between elements that have the same different functional group but in the same molecular formula. For example, let's look at this. C2H6O. Now, we can have structure of CH3CH2OH from C2H6O. This is ethanol gotten from C2H6O. This is what? Methoxyethane from ether group. You can see the difference is what? Is in the functional group. OH is alkanoic acid, whereas O is an ether, but the same molecular formula. The same thing applicable to C3H6O. We have CHO, methanol, alkanol. We have CO, none. This is alkanol. This is alkanone. Propanol and also 2-propanone. From where? The same molecular formula, but different structures. All right, let's go for a brief break. When we come back, we continue from there. Thank you.